Hi everybody, and welcome to this talk about Project Atlante, which is an experiment we have made on building Earth-scale worlds with Unreal Core tools only. My name is Alban Bergeret. I'm solution architect for simulation at Epic Game, and I've been in the simulation industry for something like 20 years, and over time I grew some knowledge about how to build a synthetic environment from geospatial data. Today, I will be with the awesome Stephen Philip from my team. Stephen?
Hey, I'm also a solution architect. I'm on the architecture team, so I help a lot of non-games customers integrate all the Epic technologies into their workflow.
Yeah. So the solution architects are Epic, which are here mainly to provide technical support to the business developer when they talk to licenses. But on top of that, we do other things, like helping the development of Unreal Engine to make it more aligned with the industry-specific needs. Part of that, we do beta testing on new engine feature. We help developing new plugins or new feature. And in order to put all of that together, we sometimes create a proof of concept project to challenge and to demonstrate such this feature. And Project Atlante is one of these projects. Why are we here today? You've seen all the fancy demos we have made internally, like City Sample, Electric Dreams. They are really beautiful, and we have another proof this morning with the keynote. Fantastic, but it's still a little bit small for what we need in the simulation range. So we ask ourselves the question, what if we wanted to achieve the same visual quality, but at a bigger scale for the whole Earth? That's the goal of Project Atlante. Project Atlante, as of today, is not a product. It's not a plugin yet. You cannot download it. It's an internal development we have been made on the UE5 main branch. It's not finished yet. But still, this experiment has already demonstrated some interesting outcome, and we are here today to explain you the idea behind this project and the early results we achieved. By the way, we make some assumptions. The Earth is not flat here. Because of that, we'll make some complicated math some maths, and we won't use any imperial systems in this presentation at all. So, thank you. So, really quickly, we have a really packed agenda, and we want to keep time at the end of this talk for live Q&A. So, we'll probably go quick on some slides, but feel free to ask questions at the end. So first, we will introduce the challenge and the reason behind the fact that we wanted to make this experiment. We discuss the existing solution that you have, and we'll go through the game changer that enable a new approach in creating that. Then we'll share the first results of our experiment, how we can make a full Earth in nanite, a full coarse Earth, I would say. And then how we can put together a streaming system that enables to inject high-resolution inset everywhere, or everywhere. Then go to a small inset, how to generate a terrain with imagery and so on. And Stephen will take over speaking about how we could use PCG to populate this environment. And then we'll conclude and leave you some time for Q&A. So first, why do we do this experiment? We'll speak about the current challenges in creating large open worlds in Earth-scale things and the solution that we have. In gaming, even if you have beautiful large open world games, it's still a small size. It's dozens of kilometers. In simulation, we often have requirements for environments that go up to hundreds of kilometers. And of course, we cannot have the same level of details. And if you go to flight simulation, it's even worse. It's the full Earth, you can fly everywhere. And these constraints give you a lot of challenges to solve related to the storage, the streaming of data, the use of geospatial data as input, and all the location of these stuffs on Earth. So why first we don't use flat Earth? Because every time you go flat, you make a projection of this sphere on something. And this projection transforms your distance. So everything which is using distance for computation, like speed, is wrong. And we don't want to have that. So to keep the accuracy, we always work in rounders. And on top of this, if you do some intersection like ballistics and so on, there is a huge difference between intersecting a flat plane and a ground surface. And even if you are flying a flight simulator, the horizon is below you at altitude. So we need to do something around Earth. So fortunately, over the last few years, some great companies have created solutions to bring Earth-scale dataset into Unreal. You have all heard about Cesium for Unreal, S3 ArcGIS Maps SDK for Unreal 2, and Black Shark Scene 3D. By the way, I quoted the presentation from these guys in this slide. Feel free to attend these talks. Don't get me wrong, I love these tools. They are fantastic, but they have one problem. They are all runtime based. What I mean by runtime based is the geometry that you see on the system is piped during the execution of your program. It doesn't go through the cooking step. When we cook an environment in Unreal, we do a lot of things. So let's take the basic example of a static mesh. When we build a static mesh, we create different visual representation, the level of details, to have it good for the visual scene, for rendering. We also build a different collision mesh for the physics part of it. It can be simple primitive or complex primitive. And we also build the mesh distance field, which is an approximate voxelization of that mesh that is used a lot for lighting in Lumen, for shadows and reflections. And of course, you have all heard about nanites that wraps everything together to have a continuous LOD system that can deal with millions of triangles. But that's not the only thing that we build when we cook something. We can also enable world partition, which is a world streaming system that creates automatically level of details of your world and make sure that they stream it in and out correctly. And on top of that, when you want to simulate entities' behavior, you need to enable pathfinding. And for that pathfinding operation to work, you need to have a navigation mesh. So we provide dynamic navigation mesh, but it's always good to cook that beforehand so that everything is ready when you want to simulate. And so if you don't cook your content, what do you miss? You miss the level of details on your geometry. So you need to have a solution that automatically takes consideration of these LODs. It's a little bit complex to build the simple collision primitive. So most of the time, this solution go with the complex collision primitive that has a performance hit for the physics. And you totally miss also the mesh distance field. So everything which is global illumination or reflection related had to go through the hardware ray tracing path. Fortunately, we have done a lot of improvement on this one, but still the software one also makes sense. Of course, you don't have nanites, so performance hit need to handle a large amount of triangle and to stream it correctly. And you don't benefit from any streaming mechanism from world partition. For the navigation mesh, you have to enable the dynamic nav mesh that is generated on the fly around the entities. So that's a certain amount of drawback. But for me, the most important one is what you pipe in is geometries. And what if you want to have an environment with not only geometries, animated objects, let's say a windmill that has a rotating wheel, or a blueprint with animation, behavior, a door that you can open and close. This solution cannot give you this opportunity. You have to create them manually. So the question we asked ourselves was, okay, how could we use Unreal Engine tools only, like world partition and such, to address the same problem and try to scale up to a gaming quality at Earth scale? So don't be too excited, it's not done. And it's not for today, but still the system we want to put together can help for high definition insets in some point of interest in your world. So what were the game changer who enabled this idea? Starting with UE5, we introduced the double precision that gives you a really good accuracy for large environments because the 32-bit floats is not enough for when you're doing with geospatial data. We also introduced the georeferencing plugin that enables you to convert from a geospatial coordinate to Unreal coordinate and vice versa. And starting with UE5.3, we had a crazy idea to bake the nanites, the landscape actor as nanite meshes. And we were really surprised. Nanite was performing very, very well for the terrain, even better than our previous landscape platform. So it means that the static meshes are not dead for the terrain and the ground. But the most important thing was Lego Fortnite. I don't know if you played this game. The map is really huge, and internally it's made of different tiles, 2D grid of tiles, each of them generated on demand. And in order to do that, we made the world partition system to evolve from supporting just one single level, like it was in the beginning, to multiple world partition levels at the same time. And each of these sublevels could have an arbitrary transform. And so it rings something in my mind. And I did this quick test just to check if it was working, because I don't trust engineers. And I took 2 world partition levels and just had a second instance of it, close to it, with 45-degree orientation. And you see that the world partition, 2 world partition levels are working at the same time. And so if we have the idea to put more terrain like that in a curved fashion, we can probably go wider. And of course, we do a lot more things with Unreal these days related to procedural content generation. You have the geometry scripting tool that enables you to dynamically create meshes. You have the PCG framework to create forest and geometries and whatever, plenty of things. And we also released a biome preset that is a layer above the PCG that enables you to create biomes at scale. So what was the approach we've been taken in this experiment? It's the Fortnite disco ball approach, the boogie bong. It's a good old stuff in simulation. We just tile terrain and stitch them together. And so we use the concept of tile. We name it sometimes a geocell. Is a tile of 1 square degree, but it can be an arbitrary size in our approach. The idea is to create one single level for each area. Each of these single level has its own world partition grid, so it has its own local streaming system. And we just spawn this level where we want, having into consideration a specific transformation coming from their geospatial origin. Of course, you don't put tiles everywhere, so you need to fill the holes. And for filling the holes, we need to have a fallback solution to have the continuity on Earth that can be coarse or that can be fine. And if it's fine, we can still use the runtime-based solution I discussed before. So we go there only for high-resolution, high-quality insets. So what do we need to make this happen? We need to know where to spawn this level. So we need to have the geospatial location of that level to know where to spawn it on Earth, on your persistent level. What is fine with this level is they are more or less flattish. It's an ellipsoid, but it's also almost flat and almost rectangle. So it's easy to work on one of these levels in the editor. And you can also use the 2D world partition grid. When we started this experiment, the 3D world partition grid was not available, so we worked in 2D. And because the level is not huge, it can still cook in an acceptable time, and it's more or less set up. So we will need to associate to every level a new information, which is its extent and its level transformation. And the idea also is to trigger events when we decide to load this level so that we can create a cutout under this level to get rid of the fallback geometry for the whole Earth. It's like a local patch of tissue. But we also need to think about the packaging. So we go with a pair, an extent, and a level, and we need to put that in an Unreal package. Should we do all of that in one single package for the whole Earth? No way. It would be a huge size, and if you want to just make a local change to an area, you will have to repackage everything. You don't want that. We want to have a DLC-based approach with different independent packages, each of these packages containing a level, the world partition level, and its extent information. And the idea is also to have an automatic discovery of the available extent in all the available package. So you don't have to think beforehand where you create your geometry. If you want to add something new, create a new package, create its extent, and the system will work for you. So the data set will be huge, so we need to store it somewhere, and we probably not fill in a local hard drive. So we need to put together a solution that has a remote storage server on a local network or whatever external solution if you can be connected, with a notion of a downloading radius. So when you are coming close to an area on Earth, you start a download process, the package gets copied on your local cache, and that way, when you come closer to this area, you just mount this package and load the demanding level. So we need to put together a system with automatically package discovery and download mechanism to your local hard drive. But before going further, we have to think, hey, before coding, let's check if it can work, actually. How many world partition level we will have to handle at the same time? If we make the assumption of a big geocell, which is around 100 kilometers, if we took 3x3 or 4x4 geocells at the same time, it's between 9 and 16, and we still have a really good visibility radius for flight simulation that does the job. So I think it's acceptable for the world partition streaming system. Then for the storage, if you take every geocell on Earth, it's 64,000 geocell. That's a lot. Fortunately, there is a lot of water on Earth, and we can just focus on the ground ones. So that's just around 20K, sorry for the numbers. And so we made some estimation of potential size for these cells, and it gave us some potential values for the number of storage, the size of storage we need to have on the server, or the number of cells you can have locally. And even it's quite a big amount of data, it's accessible for a storage server. So, okay. Now we need to think, okay, if we are flying fast, will we have enough time to download this data set on demand? So I took some example of really fast jet speeds around Mach 3, and more or less we can say we do 100 kilometers in 100 seconds. And so when we do other hypotheses about the package size we will have to download and the bandwidth of your local network, there are different downloading times. So yeah, even if you, in some combination, you have some constraint, the download time is possible. So it's worth trying. Though what do we need? We need a fallback, low-resolution global solution for the Earth. We need a top-level streaming system that will spawn these levels with an automatic extent discovery. We need to have a correctly shaped tile canvas system for the terrain to make sure that when we stitch, there is a continuity, and some PCG modules to decorate that terrain. Everything packaged correctly. So then we switch to the results of our experimentation. The Epic Blue Marble is basically an Earth ellipsoid with a nice texture. So we wrote, using the geometry scripting tool, a system to generate an ellipsoid having an eccentricity, a resolution that you want, taking into account different latitude, longitude limits, making sure we don't mess anything at the poles, and save a specific mesh asset. And so we arrive to this geometry automatically. So it can be really coarse, it can be really resolution with a high resolution, it can be with a high eccentricity, and we can define latitude and longitude limits. The idea is to go up to this level, which is a geocell, so 1 square degree. It looks like a rectangle, but no, it's an ellipsoidal part, a part of the ellipsoid with a different shape depending on when you are on Earth. Okay? So having a mesh is one thing, but we need to have a material on top of it. We need to have a texture. And if we just keep one single, let's say 16K texture for the whole ellipsoid, it will be too blurry. It's better to have a better resolution. And so we use the UDIM system that natively comes with Unreal to create really high resolution virtual texture. This one is 80K by 40K. There is a command line if you want to do that with this good old ImageMagick, but the goal is to have a ready-made tool to do that for you. And so at the end of the day, we have this fallback solution with the full Earth, entirely nanite, so you don't see any LOD popping and no texture popping. Of course, close to the ground, it's a little bit coarse, and we need to improve that a little bit by adding elevation, to probably split the global mesh into additional subtiles to increase the virtual texture resolution workflow. But at least, and of course, it creates the ability to do Boolean cutouts on this geometry to replace the patches. So that's something running. Now, the streaming system, the globe composition system. We don't want to be more clever than our engineer in world partition, so we will be using what they have done. So everything that happens inside a tile will be processed by world partition. We just have to add and remove these sublevels, and we have to decide when to do that. So the first naive approach is to say, okay, let's take just a visibility range, but later we can combine that with other more precise algorithm like an altitude value or a size on screen, whatever. So how to get this criteria of visibility range? Most of the time, the geocells are expressed in latitude and longitude space. The problem is that if you get the ratio of a distance and a longitude in degree, it's not linear. It depends on when you are on Earth. So every geocell has a different size in kilometer at altitude. I'll let you read the maths, but globally speaking, the system says that a visibility circle in kilometers translates to an ellipse in latitude and longitude space, where the ratio, the eccentricity of this ellipse, depends on when you are on Earth. So it's just a basic ellipse versus bounding box intersection problem. So we have the size of this ellipse, but where to put it? We don't want to just trim the geometry around us, because you might have an entity flying or driving somewhere else at thousands of kilometers, and this entity still needs the ground to drive on. And it's not just the camera that constrains you streaming. And for that, the world partition system has a notion of streaming source. When you attach a streaming source to a blueprint component, it acts like a seed to decide to stream the geometry around. And we can access this streaming source. So our system gathers the streaming source from all the entities in the scene and consider that for streaming the levels. The implementation is quite basic. We have a world subsystem. At the beginning of this world subsystem initialization, we gather all the possible extents information we find in the dataset automatically. Then we distribute them in a 2D hierarchical streaming grid in latitude, longitude. And each frame, we gather the streaming source, the streaming source components. We get their transformation in latitude, longitude, compute the ellipse radius, and check that against the different extents we have. And depending on that, we either download a pack file or add the new level. So on the right side, you see a new asset type, which is this extent definition that has a link to the associated level to load, and that contains the extent definition. And so when you have this working, you see on the top right the debug interface. The circle is intersecting one extent, it goes to green, and the level is loaded. If you come closer, you have more level loaded. And when you are down to the ground, you see on the left that there are some world partition objects somewhere. So world partition is working on top of that level. And if you have several tiles at the same time, you have several world partition instances, here 3, working in parallel. So live, it looks like that. You get it, we are coming close to the area, and we go further. So of course, the coarse area is coarse, but we don't want to have it nice. It can be used, one of these real-time solutions or something looking better. What is important is to have really high quality in these assets. We still need to work a little bit on that to improve our discovery mechanism, to download it from the server, to change a little bit the grid, blah, 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 but nothing fancy. It's still working. And now let's go down to a geocell. As we said, this geocell is a part of the ellipsoid. So it's not flat, and it's not even rectangular. If you want to use the landscape actor to make it, you will be failing, because that's not the appropriate shape. So we will go building static meshes. We have to pick. I need tessellation for these static meshes. And because I'm lazy and because most of the geospatial datasets are often in latitude, longitude, I went to a regular grid approach, which is totally inefficient. But remember, we'll have nanite. And nanite will do the simplification for us. So we reuse the Geocell generator for the blue marble, but clamped to a specific area. And because we want actual elevation, actual imagery, actual vector file on that, we've wrapped the GDAL library that you probably know, which is a third-party library that enables you to load any kind of geospatial data, raster, elevation, vector. And so the process is load the geotiff, reproject it to the appropriate coordinate system for your tile, resample it to the resolution of this regular grid, add the elevation from the altitude along the geographic normal, and then you end up with a nice terrain using the virtual texture imagery as mentioned before. So it's a nanite terrain, and you see the ugly regular grid, but in the middle, that's the first nanite cluster who started to pivot to another level of detail automatically. And nanite does that for all the geometry. So what you see on screen is really an optimized terrain for nanite. And the beauty of that is the performance, because you just have one big mesh and one big virtual texture. You save a lot of draw calls. You save a lot of static mesh instances, component, and so on. And the render path of nanites, so the sample runs at 120 on my computer. And if you profile, the GPU time taken to render only the terrain is half a millisecond. And only 200 draw calls. So really efficient for terrain. And here is the final result. So nanite is making sure that you don't see any LOD popping. The virtual texture system is making sure that you stream the right MIP map of your raster tile when you're flying. I think I'm flying at 3,000 kilometers per hour. And then if you look at the top left part, the world partition debug thing, you will see that some geometries from world partition are loaded on the fly. Yeah. So that's test geometries, is a red plane, but the principle is here. Okay, that's all for my part. And now I will hand it over to Steven, who will explain you how to populate this world. Thank you.
So as you could tell from all the math, Alban is actually the brains behind the project, but I was lucky enough to be invited to contribute in a more artistic piece to this project. So he's got these massive, accurate terrains that are just native inside your Unreal Engine project. But if you want to do something meaningful with it, make a flight sim, make a video game, it's going to need to have a little more life to it. So I'm here to try to help populate the world. When thinking of populating large worlds, the first thing that comes to mind is PCG. This is our procedural content generation tool inside of Unreal Engine. So this lets you create really complex systems of rules and properties to really scatter any number of types of meshes across really large areas. This is from our Electric Dreams sample that also had a small piece of that keynote. And in the perfect world, we would have these really large real-world terrains with this level of richness and density, but we didn't get there today. So I was working on a parallel path to Alban. So this is just a basic static mesh I grabbed from Sketchfab to develop initial prototypes with. It's a really basic static mesh with a basic texture map. And to try to put different types of assets in different places, I just took that texture into Photoshop and made a really simple RGB mask for the drier areas of the world and the more lush areas of the world and everything in between. So this gives me nice primitive data that I can read in a PCG system. PCG gives you a lot of methods for sampling meshes. So you can get a point for every single triangle of a mesh, every single vertex of a mesh. Or there's a sample method called Poisson sampling, where it just randomly scatters points around a mesh. So every white dot here is actually a little debug cube attached to the surface of this mesh. And there's a really important checkbox in that mesh sampler for extracting the UVs as an attribute. So every point is recording the position on the texture map, basically, and we can reuse that later on. So I can directly feed in the biome texture I made in Photoshop into this system, even though it's not being used in the material anywhere of that static mesh. And now every point is sampling the new texture, and you can see there's red points and green points and blue points that correspond. I guarantee there's a better way to do this, but this was my first attempt, and it worked fine. Every pixel in there, I just said, hey, is this point more red than green, and is it more green than blue? And those created my different biome categories that you can just use a simple static mesh spawner and create some assets over that area. So this is what it looks like. It's not to scale, as you can tell, but stylistically, I think it's cool. I would play this game, right? I sincerely apologize if your region of the Earth is not accurately portrayed, but I think you understand. Still, it's a good proving ground to show that this could make things look cool. And I could make this graph much more complex to handle, bigger areas, many more static mesh spawners and types of sampling that biomap. But I took this as an opportunity to learn our new PCG biome system. So this is something that's in Unreal Engine as of 5.4, as an experimental plugin. It is just for creating rich biomes across large areas of land, so it seems like a perfect fit. There are two plugins for this. One is the core biome plugin, and the other is a sample project, which I definitely recommend opening up if you're exploring this. It's this landscape environment with different biomes populated around. I have to warn you that it is somewhat complex, especially if you're new to PCG. So luckily, I think it's cool that all of the inner workings of that system are exposed as these individual PCG assets, but there are 50 of them, and they're just graphs within graphs within graphs. You don't have to dig this deep, but I'm going to be customizing it a little bit later. It's not just a warning about complexity. This is actually also reassuring because this is an extremely robust, modular, scalable system built by the greatest minds at Epic. So if you're interested in this, there's plenty more PCG talks this week at Unreal Fest. Because it's experimental and really complex, I can't just explain the whole thing in the next 10 minutes. So you'll have to forgive me for cutting some corners. But there's a bunch of different pieces that go into it. And the first one that you'll probably encounter would be the texture projection graph. So you can feed in a biome texture, just like that initial prototype, and define different color values for where certain biomes begin and end. And you also define like what physical size that texture is so that it can fit on top of your world. From a top-down perspective, this is what it looks like. So you have the different colors for the biomes, landscape underneath, and then all those trees and bushes and rocks get created. It does not use the landscape layers or the vertex painting of any sort, so you have to create that map in your preferred method. And for each color that you define in your biome map, you say this exact shade of blue is the coniferous forest. And that's its own asset that you put into the system. And then for that biome, you get to define an asset definition as well. This is where the complexity can kind of explode in good ways. You can just spawn simple static meshes like a pine tree. You can also spawn child assets. So maybe there's a big boulder that spawns little boulders around it. You can spawn blueprint actors. You can spawn assemblies, which are a level instance where you've pre-compiled a cool-looking point of interest. And you can even define a generator just for how those assets get scattered onto the surface. So there's a lot of flexibility there to make interesting environments. This is what it looks like in 3D. That texture projection comes down on the world and creates these 3D voxels that get populated with your biome assets. But how can this be used for a real world? We're not using a landscape system. We're not working at that small scale. The Z up is not always Z up. You know, if you're on the equator, you might be sideways. So we're going to have to make some choices there. And it would be unreasonable to have one big PCG volume for the entire Earth or pre-calculate the point of every single tree on Earth. So we need to make it a little easier to work with. The first step in this direction is a really basic blueprint actor. It has a variable for the Geocell mesh that Albin would be providing, and a variable for the biome texture that gets associated to that. And there's not too much else to it, really. It's got the PCG biome running as a component on this actor. So we could butt up all these geocells together, and they would each manage their own biome, which is a really scalable way to do it. I did have to modify several graphs, like I said, because the system is designed for landscape stuff, which is great for video games and great for like epic first initiatives. I had to go in and hunt down those different references in about 6 different graphs and change it to an actor reference or a mesh sampler or a world array hit query, just to make sure it worked for our system. And something I wish I knew earlier on when learning PCG was actor properties. So the Geocell can have a lot of good data to it, like the bounds of the mesh, the exact center point of the mesh, maybe what area and vector of the projection. Those can be stored as simple variables in blueprints, which I'm much more familiar with. And then in PCG, you can just reference that variable and say, okay, give me the mesh reference, give me the texture reference, give me the vector reference. And you don't have to come up with the math and recompute that stuff in the PCG graph, which is a little different than blueprints. So at this point, I had some really basic fake data, testing different rotations and elevations and curvature to make sure that a biome system could work and could look good. But that is not real data. So what kinds of real data can we use to inform this system? Early on, Alban shared with me this cool website called Ecoregions, where you can explore the world in the different areas of the biomes, real biomes. So you get like the tundra area and the desert area. But for our purposes, it's pretty big. You're not going to have the same tree across that vast of a space. It has a different mode in there just for ecoregions. So this is hundreds of localized regions, like central Afghan mountains. And if you were wondering, Seattle is considered the Puget lowland forest. So it's a little more well-defined, which is really informative, but still not quite to the scale that we would want. And this is where we landed on using land use data. So this is publicly accessible, like this is on ArcGIS. You can just go and get per pixel information for most places. This is a picture of my hometown, actually, and it's got here the river, marshes, the farmland, the foothills, the pine forest, and every shade of red is a different density of urban development. So there's an insane amount of data at an amazing resolution to use that in other Unreal Engine systems. We weren't rendering my hometown for this project, so Alban gave me the land use data for that piece of Montreal area that we were working with. I created 2 simple biomes, some trees for the forest, and some buildings for the urban areas. And he gave me the Geocell that I inserted into that blueprint. And this is the result. I really like how it turned out. I think it's not quite accurate, quite to scale. There's plenty of room for improvement, but it's really a promising direction to go to get a really large, believable world really, really quickly. And so I work with architecture and engineering clients. He usually works with simulation clients. But after making this, this seems like a cool way to make a really big, geographically accurate area for even video games and TV shows and things like that. So it's really cool. And we hope that we can take it a little bit farther. Some of the next steps would be swapping out my primitive test meshes with like real Quixel assets to make it a little bit closer to that Electric Dreams demo. And I'm also not making use of any hierarchical or runtime generation right now. So every tree is there all the time, when really they could be streaming out independently or actually only generating those assets when I get close. Like when you come down to the farmland, you could have grass and wheat springing up out of the ground so that it's realistic at many different distances. So hopefully we're going to work together a little bit more after this and integrate our 2 pieces of this together. I think hypothetically in the future, you could be querying these latitude and longitude coordinates and automatically getting that DEM data, the satellite imagery, and those biome definitions to create this sort of environment really, really fast. So yeah, I'm excited to see where we end up with it. Thank you.
Thank you, Tim. So let's conclude quickly before ending up for Q&A if you had. So this prototype is interesting for us because it starts to be working. And we have a working workbench ready to be improved, to integrate different work, and to go on collaborating within the solution architect team. There are different outcomes already. We have to fix some engine bugs. So in 5.5, you will see better performance in NI generation stuff and things like that. And we will pursue this effort over the next months to come later with a more visually appealing result, I would say. I'm really I'm a little bit sad because there is an area we haven't been able to touch, is the packaging one. Because we think that the monolithic cooking is not an approach we want to take. It would be taking too long and too much time. And we want to have this DLC-based approach. Actually, we put the data into separate plugins, and it's possible to package them in different individual package using the primary data assets workflow. But still, even if you have the different package, the cook process is monolithic. So you recook everything. We would just like to say, okay, can you please just cook this Geocell? And that's something that is not possible today, but the development team is working on that. And the future will be the game feature plugin, which are kind of same concept of the plugins, but with more capabilities, being able to embed code, being able to be mounted, unmounted, on demand. And that's the direction we are taking to provide incremental cooking and packaging in the future. And it's fun to make this project, but we want to deliver something to you. So what are the possible outcomes of that? So first, no commitment, because so far it's solution architect work. It's not product work, but hopefully it happens one day. We have in mind updating the georeferencing plugin to a new Geospatial plugin, wrapping around GDAL, giving you access to more raster, vector file. Imagine taking a shape file, converting that to spline at the right location and piping that to PCG. Also, this simple Geocell generator could be provided, and the streaming system in the Globe Compositor plugin too. And if you don't want to use the runtime-based solution I presented sooner, maybe the Blue Marble plugin can be shipped, but you find other good solutions on the marketplace. But still, in the short term, we'll start writing a series of dev community tutorial to explain more in detail how we accomplish that. So thank you for your attention, and hopefully the next Unreal Fest will present some update on this project. Thank you.